For each power series, I want to determine two things. Number one, the radius of convergence. Number two, the interval of convergence. Trust me, this is a lot of work. So let's take a look at the blue power series. So the blue power series, do you see that there is a -1 raised to the n? So when you see this, this is an indication of alternating series. Let's write this down, alternating series. And then this alternating series, what is the original series? The original series is an, which is the whole body of the series. So that is -1 raised to the n, and then times n times x raised to the n. And then I want to determine the an plus 1. So the an plus 1, I will explain why we do this in a minute. Because if you go back to the alternating series section, right, the way I solve alternating series, I don't use an, I use bn, because I want to take away the alternating term, -1 raised to the n. But in this section, I will just use the entire series, and I will tell you a little trick to get rid of the alternating term in a minute. And then the an plus 1 is -1. You replace the n with n plus 1, and then that is n plus 1 times x to the n plus 1. And then I want you to expand this as much as possible. So the an plus 1 is equals to -1 raised to the n, and then -1 raised to the 1, right? Keep the -1 in there. And then n plus 1, and then you have x to the n, and then x raised to the 1, okay? And then what we are going to do next is I am going to do a limit. So that limit is limit as n approaches to 0. I will do an plus 1 divided by an. So there is a ratio between the next term and the current term, right? And then I have an absolute value to wrap the entire fraction. Why do we need to do this? So the first reason we have to clear, the first thing that we have to clear is, hey, how can we take the entire body? How can we take the -1 raised to the n? Because back to the alternating series, we analyze the bn plus 1 and the bn, right? So the bn is everything else without the alternating term. So let me just do a quick math right here. So for an alternating series, do we agree that this is an alternating series? 1 minus 2 plus 3 minus 4 plus 5 minus 6, and then plus ... right? So this is an alternating series because the plus and the minus, they alternate. So when you take a fraction, let's say you take the fraction of the first two terms, you take -2 divided by 1, right? But the issue is you take the for the alternating term, there is a negative. So how do we get rid of the negative? To get rid of the negative, all we have to do is we take an absolute value of that. So this is just equals to 2 divided by 1. So as long as you take the absolute value, then you don't need to worry about the alternating term. So all you have to do is you take the absolute value. So let's see what happened when we take the absolute value. Then you have limit as n approaches to infinity, and please write the limit. Don't just start with an equal and then do the algebra. Don't. Please write the limit. And then what do we have right here? So we have the an plus 1. So write everything out. And then we are going to do some cancellation. X raised to the n, and then x raised to the 1 divided by the an. The an is the original series, so -1 raised to the n, and then we have n times x raised to the n, right? And then can you do some cancellation for me? Simple, right? So the -1 raised to the n, -1 raised to the n, and then x raised to the n, x raised to the n. So that's it, right? And one other thing I can get rid of is this -1 raised to the 1 power, right? Because -1 raised to the first power is equals to -1, and then you have the absolute value of -1 that is equals to 1. So we can completely ignore the -1. Okay, so let's go back to the problem. So what do we have left as n approaches to infinity? So we have n plus 1 divided by n, and also we have x raised to the first power. Let's just put that out there so I can separate the n and the x, right? So how do we simplify the n? So, and one more question that I want to ask is, so let me just write this first. N approaches to infinity, so that fraction is n divided by n plus 1 divided by n, right? Do I still need to use the absolute value for the n? The answer is no. Look at the power series. The power series starts at n equals to 1, right? So when n equals to 1, this fraction is always positive, so it is not necessary to keep the absolute value. However, for the x, we do. And listen to me right now. The absolute value of x plays a very important role right here. You cannot forget the absolute value. Let's do this again. For the n goes from 1 to infinity, right? So n is always positive, so we don't need absolute value for the n. Listen, for the x, we need the absolute value for x because that plays an important role when we find the interval of convergence. You must keep the absolute value for x because in this problem, there is no proof to say that x is always positive. And then we simplify the fractions. So limit as n approaches to infinity. This is a 1 plus 1 divided by n, and then times the absolute value of x. So let me give you 1 second to tell me what happens when n approaches to infinity. The 1 is divided by infinity is equals to 0. 1 plus 0 times absolute value of x is equals to absolute value of x. So the limit is finished right here. And then the next step leads you to the interval of convergence. We have to say that this absolute value of x is less than 1 to make the series convergent. Now, you are going to ask a question. Hey, professor, you just say that the absolute value of x, I get it, but you have that less than 1. The 1 is from the middle of nowhere. How come you don't say that can be less than 2? That can be less than 5. That can be less than 1 million. Why is that must be less than 1? So let me explain why. Look at the series right now. So what do you see in that series? So that is x raised to the n, right? So if you consider the term itself, what do you remember? If you only consider the x raised to the negative n, do you still remember this? So back to a power series, you have r raised to the n power, right? I was trying to use pen, not a highlighter. So we have the absolute value of r raised to the nth power, right? So that is a power series. Okay. R raised to the nth powers, not power series. So you have to remind yourself geometric series. Right? So for the geometric series, in order for a geometric series to be convergent, what must be satisfied? The absolute value of the common ratio must be less than 1. So what is the series right here? We have x raised to the n. So this is my common ratio, the base. Look at the original series, x raised to the n, right? So x is my base. That is, if you consider that term itself, that is actually a geometric series. So for a geometric series to be convergent, and we are trying to work on convergence, we have to let the absolute value less than 1. Now, back to your algebra. The absolute value less than 1, how do you solve that? So when the absolute value of x is less than 1, so the absolute value of x less than 1, this is algebra. That means x must be between -1 and 1. All right, so now you have a lot of work to do. So you have to test the endpoints, the interval of convergence, because the endpoints, they do not always converge. So what happens when x is equals to -1? So when x is equals to -1, which is right here. So what do we have when x is equals to -1? We have n goes from 1 to infinity. So that means you have to plug in -1 to the given power series. So that is -n raised to the n times it was supposed to be x raised to the n, right? But x is equals to -1, then you have -1 raised to the n. So you have -1 raised to the n. Do we agree that we have 1 right here and then 1 right there? All right, so that is the same thing as, so let's see how good your law of exponent is. So n is equals to 1 raised to infinity, and then the n is n, and then -1 raised to the n, -1 raised to the n. So let me test you this. Let's say we have 2 raised to the n times 2 raised to the n. What is that equal to? That equals to 2 times 2 raised to the nth power, right? So in here, that equals to -1 times -1 raised to the nth power. And then, what do? -1 times -1 is equals to 1. So overall, you have n equals to 1 to infinity. And then, n. Another way to think about this is when n is equals to 1, you have negative 1 times negative 1, right? So that will be cancelled anyway. When n is equals to 2, you have negative 1 raised to the second times negative 1 raised to the second, which is 1 times 1. So you have a 1n anyway. All right, so we have this. And then how do we test this series? So to test this series, you have to use a very fundamental technique that is called test for convergence. So use the test for convergence. And then, so we have to take the limit as n approaches to infinity of this n right there. So what is that equal to? That is equals to infinity. What does that mean? So this is 1 plus 2 plus 3 plus 4, right? And then if you check the last couple terms, they are something that is so close to infinity. That means if you only consider the sum of the last few terms, they are already big enough to give you an infinity. So that means the entire sum is equals to infinity. So therefore, the series diverges. Okay, so that we just test the x equals to negative 1. And then we are not done at all. We also have to test when x is equals to 1. So we have the sum n equals to 1 to infinity, negative 1 raised to the n, and then n times, you plug in a 1 to x raised to the n, so 1 raised to the n is just 1, right? So overall, that is n equals to 1 to infinity, and then negative 1 raised to the n times n, and then this is another alternating series. So this time we have to check the bn plus 1 and the bn. So when n is equals to 1, the bn is just n, and then the bn plus 1 is equals to n plus 1. So when n is equals to 1, can we prove that bn plus 1 is less than or equal to bn? So when n is equals to 1, this is 2, this is less than or equal to 1. So it looks like this is not true. What about number 2? The limit as n approaches to 0 of bn equals to 0. So that means, okay, let's write another limit. So that is the limit as n approaches to infinity, n, is that equal to 0? The answer is no, right? So that means number 1 is fail, number 2 is fail. So overall, this is divergence using the alternating series test. So let's draw a conclusion. So here is my conclusion. I have a number line, and then this number line stands for my x value. And then what number do I put on the number line? So you go back to your work, and then you drop this down. Negative 1 and 1. So negative 1, and 1. And can x be equals to negative 1? The first one that we just test, the answer is no. When x is equals to negative 1, so when x is equals to negative 1, we have a divergence, right? When x is equals to positive 1, we also have a divergence. So this is an open circle, and then this is an open circle. So that means we say that the interval of convergence is right here. Is x is between negative 1 and 1. So x is between negative 1 and 1. Or you use the interval negative 1 to 1. This is called an interval. You are taking a calculus class, so I expect you to know what interval is. What about the radius? So this is 0, right? We have a 0 right here. So half of that, the radius, is equals to 1. All right, so that is the end of the first problem. I know it's a lot of words, so you better do your homework and get enough practice. But not every single problem is that long. Some problems are long, but it's a lot of fun. So this is our first problem. First problem is always slow because it takes time to understand and to explain stuff. So be patient. Let's do number 2. So number 2, I remember I use a purple, right? So number 2, we have the summation n equals to 1 to infinity, x raised to the n divided by 2n minus 1. So this is not an alternating series. So therefore, I will just use the ratio test. So for the ratio test, I have an equals to the entire series. And then the an plus 1 equals to x to the n plus 1 divided by 2n plus 1 minus 1, right? So that is equals to x to the n times x to the 1, and then 2n plus 2 minus 1. 2 minus 1 is just equals to 1. So we have both, and then we just take the absolute value and then compare the ratio of the n plus 1 and the an. So we have limit as n approaches to infinity, which compare the ratio. So when you take when you use an absolute value to wrap the entire fraction, then take away all the negatives. So that is limit as n approaches to infinity. We have this one we don't need to make the fraction bar so long because we are going to do it reciprocal. So we have x to the n, x to the 1, and then 2n plus 1 multiply, divided by a fraction is multiply the reciprocal of that. Don't tell me you don't know how to do it. So x raised to the n, and then 2n minus 1, and then we do some cancellation, x to the n, and then x to the n. That's all. And then what do we have left? Limit as n approaches to infinity. So we have 2n minus 1 divided by 2n plus 1. It doesn't hurt to keep the absolute value. And then we also have an x left. So how do we take care of the 2n minus 1 and the 2n plus 1? You learned that at the very beginning, right? So since the highest degree of the exponent is 1, that means you divide each term by n raised to the first power. So back to this problem, you have limit as n approaches to infinity. You have 2, right? Minus 1 divided by n, 2 plus 1 divided by n, and then times x. Again, it doesn't hurt to wrap the fraction using an absolute value. So once n approaches to infinity, what do you have left? You have the absolute value of 1 times the absolute value of x, which is just the absolute value of x. We must keep the absolute value and must say that it's less than 1 to make the series converge. Now, you might ask me again, hey, why do we have a minus 1 right here? How come this, no, sorry, not minus 1. How come that is less than 1, but not less than 10, not less than 3, not less than 5? That's the reason why you have to watch my video, like the video, and subscribe to my channel, right? Do you still remember your power series? So for the power series, do you still remember that there is a common ratio and then raised to the nth power? In order for the geometric, did I say power series? Geometric series. In order for that geometric series to be converged, what must be satisfied regarding the common ratio? So the common ratio must be less than 1. So here, my common ratio is the base x, right? Look at the power series. Look at the circle. X raised to the n, right? So the base is x. That means the common ratio is x. So in this problem, we have to make the common ratio x less than 1 in order for the series to be converged. So that's why it must be less than 1, but not less than 2, but not less than 3. It's because the geometric series, the absolute value of the common ratio, must be less than 1. And then you solve the inequality, so that is negative 1 less than x and then less than 1. So that generates two endpoints. The first endpoint is when x is equals to 1. We have to test the endpoint because for the interval of convergence, we cannot guarantee that the series is convergent when x is equals to 1 and the series is convergent when x is equals to negative 1. There is no guarantee. That's why after you figure out the inequality, you must test the endpoint. Okay, so when x is equals to 1, you plug in 1 to the given power series. N equals to 1 to infinity. 1 raised to the n, that was an x, divided by 2n minus 1, so the top is just a 1, right? So n equals to 1 to infinity, 1 divided by 2n minus 1. This one you can use a comparison test. Alright, so using a comparison test, we have to compare the 2n minus 1 to what? To 1 divided by 2n, because that minus 1 doesn't matter when n is so big. And one other thing is you don't even need to worry about the 2. You can just compare that with the n. So this will be a diverge, right? So this is harmonic series and diverge. So diverge means an infinity. So we have an infinity Can a real number be greater than infinity? No. So this one has to be infinity. So this is a diverge. So overall, this series is diverged using the comparison test. And then also, when x is equals to -1, so x is equals to -1, we test the left end. Oh, that generates an alternating series then. So this is -1 raised to the n and divided by 2n minus 1. So this is an alternating series. Then you have to do the bn and the bn plus 1. So the bn is 1 divided by 2n minus 1. And then the bn plus 1 is 1 divided by 2n plus 2 minus 1. So 2 plus 1 is 1. So 2 minus 1 is 1. And then when n is equals to 1, can you prove that bn plus 1 is less than or equal to bn? So when n is equals to 1, we have 1 divided by 3. And this we have 1 divided by 1. Oh, that works. Number 1 is true. And then what about number 2? The limit as n approaches to infinity of bn is equals to 0. So limit as n approaches to infinity, 1 divided by 2n minus 1. So that is 1 divided by infinity equals to 0. Wow, that is true. That is true either. So that means on the left end, the series is converged using the alternating series test. So let's draw a conclusion to summarize what we found. So we have a -1 and a 1. And then when x is equals to -1, we have this. So this one, I don't want to draw a mark. I want to draw a solid point. And then this is an open circle because when x is equals to 1, so look at the first test. We have a diverge, right? So this is a converge. And then when x is outside of this interval, we have a diverge. We have a diverge. So that means the interval of convergence is between -1 and 1. So this square bracket means x can be equal to 1. So using an inequality, so that will be having an equal. All right. And then what about the radius? The 0 is right here, right? So the 0 is right here. So the radius, half of the length, is equals to 1. All right, so that will be the end of number 2 and is also the end of this video. How was my instruction and explanation? Good? If so, let me know in the comment section below. Please like the video for me. I really want to let the channel grow. Subscribe to my channel, share the video for me. I'm sure many people are learning power series right now. Thank you really much. I see you all in the next lesson. In the next lesson, let's do more power series. All right, see you there.